Hey guys, in this lecture we're going to be studying Table J, the activity series, but also we're going to look at voltaic cells, which is going to be new for you guys, and we'll even study electrolytic cells. The bookwork associated with this lesson is 37 to 46 on page 168, and our aim today is, what are electrochemical cells? Please copy down these two now questions, which we'll answer in class. All right, so Table J. Just as a refresher, Table J has a listing of metals, and the most active metals are the ones on the top of Table J. So the most active one is lithium, and the least active metal is gold. And if you're paying very close attention, you might notice that lithium, rubidium, and potassium, the three metals at the top of Table J, are all in group 1 together, and that means they all have a very low ionization energy. So that's what they have in common. But having this very low ionization energy means that they're going to react very easily. And this is what is meant by saying that Table J is about activity. It's about reactions. In terms of details, things you should know is that any element at the top of Table J can donate electrons to any element below it. And likewise, any element that's below another element on Table J has the ability to receive electrons from that element. For instance, let's consider zinc versus copper, which I've highlighted here. And since zinc lies above copper on Table J, then I know that it can donate electrons to the copper. That also tells me a lot of information about who's going to be oxidized and who's going to be reduced. So zinc lies above copper, zinc will give electrons to copper. Giving away electrons is oxidation. And as copper receives those electrons, it's going to be reduced because the gain of electrons is reduction. And on this slide, I'm going to introduce voltaic cells. Voltaic cells are really, we can think about them as batteries. Basically, we use batteries because we are trying to store electricity, right? And the reason why we have redox reactions is that they can move electrons from the oxidized species to the reduced species. Therefore, if we are just able to intercept the electrons on their way from the oxidized species to the reduced species, then what you've got is electricity. So batteries, which are voltaic cells, have two electrodes, here and here, and one of those electrodes is the site of oxidation. In this case, it'll be zinc. And the other electrode is the site of reduction. In this case, it'll be copper. Allow me to explain. So since the zinc is higher on Table J, then that means that it's going to be donating electrons to the copper. So that means that the zinc is the site of oxidation. On the other hand, the copper electrode is receiving electrons from the zinc, which I can prove by showing that it's lower on Table J. So as it receives those electrons from zinc, then that means that it's the site of reduction. And lastly, on this slide, you should know that it's the wire that makes this really special, because as the zinc electrode loses electrons, it forces them to travel along the wire, and as they travel along the wire, they're able to power electrical devices that lie along that wire. Okay, so this is my details slide, and it is animated, which you can't see here, but I'll show it to you in class. So the first thing I want to point out is that the anode is always the site of oxidation, and you can remember this little mnemonic device because you can think about an ox. So an ox, anode, oxidation. On the other hand, you could think about a red cat for the cathode. Reduction always occurs at the cathode. So definitely remember an ox and red cat. Both of those are super important. Otherwise, we need to remember the salt bridge. The salt bridge is basically there to make sure that the law of conservation goes off without a hitch and that charge is conserved. So the story begins as one of these zinc atoms loses a couple of electrons. So when that happens, what you're going to get is you'll have one fewer zinc atom and you'll have two fewer electrons. So I'm crossing those out. but they're going to sort of float out into the solution, and you'll get a zinc ion and 2 electrons. These 2 electrons are going to go along the wire, so I'll delete those. And then they're going to end up in this part of the cell. And what they're going to do there is they're going to bond to a copper ion, which is already dissolved in solution. And when that happens, it will reduce the copper ion to a copper atom. So you're going to get this extra copper atom, but of course you're going to be missing those copper ions, and then the 2 electrons are going to be involved in the atom as well. All right, so the other 2 things that happen are, in the left-hand side, we had an overall loss of 2 electrons, and on the right-hand side, we had an overall gain of 2 electrons. So that's not going to be good in terms of the law of conservation. So what happens from the salt bridge is that we're going to replace these 2 lost electrons with 2 negative charges from the salt bridge, and it looks like we're going to get 2 nitrates. And on the right-hand side of the reaction, we had an overall gain of 2 electrons. So that's also not cool, and we need to counteract that with a gain of 2 positive charges, which in this case it looks like sodium ions are going to come in. So we'll gain 2 sodium ions to make up for the gain of the 2 electrons. So this process just repeats, and over time, things that you're going to notice are that zinc atoms are becoming zinc ions and dissolving in solution. On the other side of the reaction, you'll notice that copper ions are reduced into copper atoms and stick to the electrode. So overall, the way that this battery would die is if it runs out of this anode to oxidize, or if it runs out of ions in the solution to be reduced. Additionally, if it were somehow to run out of salts in the salt bridge, then that would also break the battery. And so with that, we've reached the pair up. So please copy down these questions for the pair up. Don't answer them. And in addition, let's go over this from electrolytic cells before the summary. So first of all, we have 2 different kinds of batteries. We have the voltaic cell, which we just went over, but we also have the electrolytic cell. First of all, they're both redox reactions, and in both cases, the anode is the site of oxidation and the cathode is the site of reduction. And in both cases, the electrons flow from anode to cathode. But there are 2 important differences. Firstly, the redox reaction in a voltaic cell is always spontaneous, but it's non-spontaneous in an electrolytic cell. And secondly, in a voltaic cell, the anode is negative and the cathode is positive, but in an electrolytic cell, the anode is positive and the cathode is negative. So the 2 major differences are about spontaneity and the sign of the anode. The anode will be negative and the cathode will be positive in a voltaic cell, but it'll be the opposite in an electrolytic cell, where the anode is positive and the cathode is negative. And that leads us to our summary. So copy down these questions, including these diagrams, and we'll answer them in class tomorrow. Thanks for watching.